Hello friends, we're still on the series on chemical bonding, but because of the fact that we want to cover key areas that serve as prerequisites before we begin to talk about the different types of chemical bonding, that is why we're still on the issue of matter, because there are still some gray areas in the issue of matter that we need to clarify before we can make progress. Okay? So today we are still going to appreciate the different states of matter and how the acquisition of kinetic energy by molecules and particles of matter can lead to phase changes in the matter. Okay, so we're talking about states of matter, which is of course prerequisite to understanding chemical bonding. All right, so we have 4 states of matter. As a matter of fact, we know that before now, at the basic level, we were taught that we have 3 states of matter. However, discoveries have shown that there is a 4th dimension to phases and states of matter. So the 4 states of matter are the solid, the liquid, the gas phase, and of course the plasma or the plasma phase. Okay? But it is important to recall that in the last video we made mention of what we call the kinetic theory of matter. And of course, kinetic theory of matter told us that particles of matter are constantly in random motion. And this motion continues to even increase as the average kinetic energy of these particles increase as well. So when you subject a system or a matter to high temperature, the particles or molecules that consist or compose that matter absorbs more energy, and that increases their average kinetic energy, and that also in turn increases how fast they are moving. And as they are moving faster as a result of increased kinetic energy, those particles tend to move away from each other. And this distance that is being made as particles begin to move faster, as they absorb extra kinetic energy, leads to changes in the states of the matter, or what we call changes in the phase of matter. Put in another way, all the particles that make up matter are constantly moving randomly. However, when heat or energy is supplied to the system or to the matter, each of these particles absorb the heat, and that ultimately increases what we call the average kinetic energy. This is because all the individual particles have different kinetic energies. They are moving in different motions and at different speeds. So as you increase the heat of a system or a matter, the particles gain increase in their kinetic energy, and that ultimately increases their average kinetic energy, since each of the particles is moving with different speed and with different energy. And as the average kinetic energy of these particles increases, they tend to move faster and further away from each other, and the distance between these particles, as it continues to increase, you're going to have matter changing from one physical state to another. In the case of water, you have water changing from solid to liquid to gas. This is critical because you have to understand that there are certain attractive forces that are holding these particles together, but subjecting it to temperature or supplying energy or heat to the system, of course, destabilizes those attractive forces, and this is because particles now begin to move away from each other. That is what we understood from the kinetic theory of matter. Okay? So ultimately, to buttress what we just analyzed, it is important to understand that as you increase the temperature of a system, that the kinetic energy of particles actually increases. Put in another way, as you subject a system to high temperature or a matter to high temperature, the average kinetic energy of all the particles increases and they move faster and farther away from each other. And that ultimately leads to changes in the phase or state of the matter. So conversely, or the vice versa, is what you have when you begin to decrease or reduce temperature. By cooling, once you begin to cool matter, what happens is that those particles begin to lose their kinetic energy. And of course, they begin to move slower. And as they are moving slower, they begin to come back together. And whatever attractive forces that held them in place, the molecules in place have been issued, is regenerated. Just like in the case of water, what hold water molecules in place is hydrogen bonding. As you begin to subject water molecule to high temperature, those bonds begin to loosen up, and of course particles or molecules of water begin to move apart, and it changes from solid to liquid. You keep subjecting it to high temperature, of course it vaporizes into gaseous phase, and ultimately those hydrogen bonds are broken. But when you begin to cool the water molecules, of course it condenses back, and the hydrogen bond holding those molecules begin to regenerate until, of course, you get water back to the liquid and back to the solid phase. All right? So as you decrease the temperature of a system or a matter, of course, you decrease the kinetic energy. You slow down the motion of those particles. All right? Nice. So to typify all of these that we have explained, you have matter in the three different physical states. You have the solid, liquid, and gas. All of these, depicted in container A, B, and C. Of course, if you look closely in container A, you notice that particles of matter are lumped up or stacked together. They are touching. They are closely packed in their crystal. And as a matter of fact, you notice they are not moving freely. However, they are vibrating within. Those particles are vibrating within the mix in the solid system. All right? So in the solid phase, particles are more closely packed. They touch themselves. They are closely packed. All right? They are jam-packed within that matter. All right? This is nice. But once you begin to subject the solid particles or the particles of the solid matter to high temperature, increase the temperature, of course, I said it, all the particles begin to move even faster. It's no longer just vibrational motion now. You can even have them going into rotational and translational motion because they absorb more kinetic energy and they begin to even move further away from each other. And when they do that, you see them changing. You see the solid particles, of course, breaking down into liquid particles. That way you see that those liquid particles are moving faster than they were when they were in the solid state. So here you say that the degree of disorderliness of liquid particles is higher than the degree of disorderliness of the solid particles. And if you continue to subject the particles of liquid even to higher energy or temperature, of course the particles tend to even move faster than they were moving before. And then you vaporize them into gaseous phase, where you have more space between all the particles because they are moving further away from each other as the average kinetic energy increases. So you agree with me right now that there is more chaos or randomness in the gaseous phase than you have in the liquid phase and that you have when you compare it in the solid phase. And that degree of disorderliness or randomness of a system in chemistry is known as entropy. It's known as what? Entropy. So your examiner may wish to know the degree of disorderliness in these three physical states of matter. Of course, you will be able to tell your examiner that gaseous particles have more entropy than what? Liquid particles. They are more disordered than liquid particles, and in turn, the liquid particles have more entropy than the solid particles. And this is key because it helps us to understand the different characteristics or properties of all of these, of water molecule, for instance, in the different phases. Okay? So entropy is the degree of chaos or randomness of a system. All right? And of course, you cannot talk about particles moving away from each other we are talking about energy or kinetic energy. Okay, so entropy is a property that tells us about the average energy, all right, that is spread apart within a matter, of course, by the particles of that matter in the microstates. So this is important you understand it. So in summary, the gases or gaseous phase has more degree of disorderliness or more entropy than the lipid, and lipid has more entropy than the solid. This is key so that you understand that there is more attractive forces binding particles of solid together than you have in lipid particles. Then, of course, there's least attractive forces acting on gaseous particles. All of these are as a result of the average kinetic energy of the particles. All right, nice. Okay, so solid, of course, have certain characteristics or certain features that helps us to say, yes, this is solid, this is liquid, this is gas. As a matter of fact, the solid particle or the solid have a definite shape and, of course, has a volume. The volume of a material tells you about the amount of space it can occupy. Okay, so solid materials have definite shape and definite volume. Of course, they have high density. Density is a property of matter that relates mass to volume. So here you are talking about the relationship between the mass, the amount of stuff or matter in an object, relating to the volume or space it can occupy. That is the density. So you have that solid particles, of course, solid matter have high density, and of course, solid matter is not fluid. It doesn't flow, all right, because they are stacked and compact together. They don't flow. Okay, and all right, they only vibrate within the lattice or within the mix. All right, so you can also say that they are not compressible because there are no spaces between them, so you cannot even apply pressure on them for them to even come closer together. All right, which is what you have in the gaseous phase. The gaseous phase, the degree of disorderliness or randomness or chaos is much, so you can apply pressure on those particles and they can actually come together. That way you say you are compressing it. Okay, so for the lipid, okay, it doesn't have a definite shape. All right, lipid has no definite shape. Okay, and of course it has medium to high density. Okay, and of course lipid is fluid, it flows. This is because the particles are moving faster and farther away from each other, so they can flow from one end of the container to another. So you say they flow. All right, again, liquid is not compressible. You can't compress liquid. Even if you can, it's going to be slightly compressible. All right, however, you also have that liquid has a definite volume. So liquid can take a particular can occupy a particular volume of a given container. That's why in the chemistry lab, different liquids have different volumes of their container. Okay, nice. So here in the gaseous phase, they don't have definite shape, they don't have a definite volume. All right, so gases just take the shape of the container, all right, that they exist in. All right, they don't have a definite volume. Of course, they have low density. Okay, they have low density, and of course, again, gases are fluid. They flow just like the liquids, and of course, they are highly compressible. I've said it. They are highly compressible because of the spaces between them is huge, is much. So you can actually apply pressure and force those particles to come together. That is called compression. Now, permit me to explain or say that at the lipid phase or state of matter acts as what we call the boundary condition between the solid phase and the gaseous phase or states of matter. I want to repeat it again. I said that the lipid phase of matter acts as the boundary condition between solid states and the gaseous state of matter. This is because there is a characteristic or a feature of solid that is found in liquid, and there is also some attributes of gases that are also found in liquid. All of these, again, recall, is dependent on the degree of disorderliness, which is a measure of the average kinetic energy that those particles have. that make them to, of course, want to spread as far apart as possible. Far to spread afar or move away from each other as far as possible. All right, nice. So the boundary condition here is that if you look closely, you will notice that liquid, just like the gases, flow. All right. Again, if you look at this closely, you notice that solid is not compressible, and of course, liquids are not compressible. So that's why we say that liquid acts as a boundary between the two other phases of matter. Nice. Okay. Again, I repeat myself. You discover that liquid flow just like gases flow. So this is a synonym. This is a similar characteristic. Again, you notice that you cannot compress liquid, and as well you cannot compress solid. So liquid has a bit of this feature and a bit of this feature. That's why we say that liquid is a boundary condition between the three major states of the other two major states of matter. Nice. So I told you in the last video that you cannot talk about matter in isolation. Whenever you talk about matter, you talk about the effect of energy on matter. All right. So as we continue to play around with temperature, you're going to have matter change in what we call the phase or states. It changes from one phase to another. Recall the law of conservation of mass states that matter can neither be created nor destroyed. But you can have it changing from one form to the other, from one state to the other. Just like energy can neither be created nor destroyed, but you can convert energy from one form to another. So once you begin to play around energy or play around with temperature around a matter, you're going to have changes in phases. All right? Nice. So here, you see my diagram here. When you subject liquid to very high temperature, of course, you're going to have when you subject solid to high temperature, you're going to have that solid coming down to liquid form in a physical process known as melting. Okay, and of course, if you cool down the liquid and allow it to cool or subject it to cooling, of course, you're going to ultimately change the liquid back to solid in a process known as freezing, and that happens because liquid can change to gas and gas to liquid, okay? In the process of evaporation, where you subject liquid to high temperature, it changes or vaporizes to gas, and of course, on cooling, it comes back in form of back to liquid in the process of condensation. That also happens between the gaseous phase and the solid phase. Sometimes solid can change ultimately from solid to gas without going through the liquid phase in a process known as sublimation. The same way, gases can directly change to solid without going through the liquid phase in a process known as what? Deposition. So these are the different ways that matter can change phases or states. All right? So once you begin to play around with energy or temperature around matter, you're going to have the kinetic energy, average kinetic energy of those particles moving, increase, and of course particles move faster. And as they're doing all of that, there's change in their physical state. Nice. I believe it's making sense. So matter will always undergo changes, and those changes that matter will undergo are categorized into what we call physical changes and chemical changes. Okay, so in the physical changes, it's going to result in matter, the same matter, changing into another form. So you're going to see perhaps change in appearance, perhaps change in physical state, just like water. Water can change from solid to liquid to gas. Okay, this is known as a physical change because it's just water is water in all the three states of matter. So what just happens is that it only changes from one physical form to another. That's called a physical change. It doesn't involve chemical reactions, so to speak. Okay, so when you talk of physical change, it results in different form of the same substance, and you can see physical change, typified by way of color. Okay, you can see the matter changes, of course, in color, and of course you have maybe varying size and shape of the matter. That's a physical change. Okay. However, in chemical changes, one of the ways to know that chemical reaction is happening is also a change in color. All right, so we're going to talk about that as we proceed. But just know that when the physical appearance of matter, is altered, definitely you're going to have a physical change. Perfect example of that is when you dissolve salt in water. When you mix it, you're going to have a salt solution. But even though you have a salt solution, but what you still have there is salt and water. How? When you vaporize the salt solution, you're going to still have your water, and of course you're going to have your salt in the container. Of course, you can collect back your water. So what we are trying to say is that physical changes are easily reversible. All right, these are easily reversible. This is because no chemical bonds are broken or formed in the process. All right, so play around with temperature, you're gonna get back your particles in the physical change. Nice. But in the chemical change, ultimately you're going to generate a whole new substance, okay? Because a chemical change involves chemical reactions. In fact, as a matter of fact, in chemical change, there is redistribution of valence electrons, all right? Atoms may wish to transfer some of their valence electron to the other atom, to make a covalent bond. Some other time they share to make a covalent bond. So the reactants or the starting materials ultimately will generate a new product. All right. So the substances on the left hand side will generate entirely new substance at the right hand side of the reaction. So chemical change will always result in completely new substances, and this is because of a result of chemical reaction. And this is, in most cases, cannot easily be reversed. Take sodium, for instance, sodium metal. It is a very hard reactive metal. Once it comes in contact with water, it can ignite, and with a lot of, noise and vibrations. Very reactive metal. Okay, so it's very reactive. And chlorine, again, is a very dangerous gas. If you inhale chlorine in sufficient amount, of course it can kill the person. So it's a poisonous gas as an element, okay? Also diatomic gas is poisonous. The same thing, this one is very reactive, and these two substances, of course, for instance, are not good for humans. However, but when both of them are held together by chemical bond to make this compound called sodium chloride, it now happens to be part of what we put in our meal. That's to show you that the sodium chloride that is produced is entirely new stuff from, of course, the parent elements that comprise or make it up. Do you see? So today's sodium chloride is not poisonous, all right, because it's part of what constitutes our food, okay? And of course, when you eat it, these things are broken in our bodies, and they help us to make other important biomolecules that keep our life going. So at the reactant side, these elements or these substances are dangerous, okay, for human consumption, all right? But at the product side, it generates entirely new stuff that is very tasty, that makes our food delicious, and as well, when it enters into our system, broken down, some of these things act as cofactors that work with enzymes, and of course, some of these things, generate certain important acids that help us to, of course, in digestion and all of that. So in the left hand side, these are entirely new stuff, entirely different stuff. In the right hand side, he has generated a entirely new product or a new chemical substance. So you see it. When this happens, of course, there is a chemical bond, because what generated it is that this atom redistributed its electrons with this by way of transfer of electron to make an ionic bond or an ionic compound that you can see. This is why I'm taking my time to explain this, because all of these things are interrelated. You see, I'm talking about a kind of chemical bond known as what? Ionic or electrovalent bonding. And we're still talking about matter. That is why I'm taking my time, and I challenge you again. If you have a brother, a sister, a sibling, a ward that is struggling with basic aspects of chemistry, I implore you, invite them, let them follow my page. By the time I'm done with the series on chemical bonding, it's going to make a lot of sense, and your chemistry is going to get better. Please, if you are getting value in what I'm saying or teaching already, kindly like, share, make your comment, and of course share my video so that it can get to those students that require some of the knowledge that we are dishing out to you today. Okay? So finally, the last phase of matter is the plasma phase of matter. All right? Recall that according to the Bohr model of the atom, you have your nucleus centrally placed, okay, with electrons that are flying. You have your nucleus centrally placed, and you have electrons that are orbiting the nucleus, of course, in different shells. All right? So here is your nucleus that contains your protons and the neutrons, okay? What actually holds an atom in place, all right, is the electrostatic attractive forces between the electrons and, of course, the protons within the nucleus. That's what makes an atom in place, all right? So when you subject solid to high temperature, it changes to liquid. When you subject liquid to high temperature, it changes to gases. But for some gases, when you continue to further subject them to higher temperature, what happens is that the atom, those gases becomes what we call ionized gas. They become what we call what? Ionized gas. Because what happens is that if this is chlorine atom, for instance, which you know is a gas, all right, and you subject it to very high temperature, what happens is that it gets to a point, it becomes so hot that the electrostatic attraction that holds in these electrons, or making the electrons, bonded to the protons within the nuclei of the atom, the nucleus of the atom, you break that electrostatic force, that some of the electrons begin to fly apart or fly away, all right, from the atom. So what you ultimately now have is electrons, flying away. Of course, electrons are negatively charged because some of the electrons of this atom have been taken away from it. Of course, the atom becomes positively charged. So at the end of the day, when you plasmalize a gas, what you have done is that you subjected it to a very high temperature, and some of these electrons are torn apart from the atom in the first place. Of course, the atom becomes positively charged with negative electrons, swimming around all over the places. So you can ultimately say that plasma is an electrically charged gas or an ionized gas. So in the plasma state, you subject gas to very hot or high temperature to the extent that you're able to take off some of its electrons. Of course, that gaseous atom becomes positively charged, and those electrons that have been ripped apart and negatively charged, all of them make what we call a soup of positive and negatively charged ions, which are made when one or more electrons are torn free or broken loose from an atom of a gas when you subject them to very high temperature. That's the plasma state. At the plasma state, you just have seas of positive and negative electrons. As this is because you subjected the gaseous matter or atom to very, very high and hot temperature, that the electrostatic force holding the nucleus and, of course, these electrons in place are torn apart. So you ionize the gas. So that's what we call the plasma phase of matter. All of these happens as you continue to play around with what? Temperature. Nice. So because plasma particles have electrical charges, they can now be said to conduct electricity. And because they have positive and negative poles as well, magnetic fields can also have some effect in them. So you see it? And this understanding is what you need, because sometimes your examiner will wish to know what is the difference between the gas phase and the plasma phase. What's the difference between the gas phase and the ionized gas? You tell them the difference is because the plasma phase or the ionized gas is just a soup of negative charge and what? Positive charge particles that are swimming around all over the places. All right? And because these charges are flowing, it means that plasma conducts electricity, but gases cannot conduct electricity. That is the major difference. Another key issue here is that plasma can, have effect, or magnetic field can have effect on what? On plasma cations and what? Anions. This is very key. So you see it ultimately in summary that because of subjecting gas to very high temperature, you were able to even break that electrostatic forces that is even holding the atom in place. That force that holds electrons, completely, the nuclear charge, that the nuclear pull that exists between the nucleus of the atom and the electrons can be torn apart when you subject gaseous particles to even higher what? Temperature. So I believe it's making sense. So whatever physical phase of matter you have, there are some sort of forces that are holding their particles together. To get those particles move away from each other means you're going to break those attractive forces, whether they are covalent, or whether they are chemical bonds, or in most cases, weaker attractive forces, van der Waals forces, electrostatic forces, and all of that. So this is what we need to explain, so that when we start talking about different kinds of chemical bonds, you understand the correlation, relationship between those chemical bonds and, of course, the average kinetic energy of those particles. I believe you learned something. Please, if you learned something, kindly like, comment, share, so that you can get to other students that need this. All right? I thank all of you for being part of what we are doing. This is my page, Chem Class with Dr. Luther. We are not going to be in a hurry to explain the basic and fundamental aspects of chemistry. We're going to take our time and speak to our students in the language they will understand. Until the next time, stay safe, stay away from trouble, and keep enjoying and learning chemistry. Bye.